Okay, so once again in this problem we have our parallel plates. We're going to accelerate some electrons through them. They're going to start moving. They're going to now enter the double slit situation, and then they're going to create this pattern on the back of high density, low density, high density numbers of electrons. Okay, let's go ahead and start this one up. First question, how are we going to find the velocity of these electrons through parallel plates? So this is an old problem that we've done many times. Okay, it's just been a while. E initial equals E final. But our final exam's coming up, right? So you should know how to do these. E initial is, what's the energy initial? Okay, UE. And what's the energy final? KE. So what's the equation for UE? QV. Okay, it's not 1/2 QV. Be careful, that's for capacitors. QV equals, what's the unit? What's the thing for KE? Make sure you keep your V straight. Remember, this is a V for a volt. This is a V for a velocity. Okay, so let's do this. So QV equals 1/2 mv squared. So 1.6 times 10 to the negative 19 times our voltage, which was 120, equals 1/2 911 10 to the negative 31st times V squared. Solve for V. Help me out, guys. We're running short on time. Something times 10 to the 6. 6.449. Let's just go to 5. 6.5 times 10 to the 6 meters per second. Good? All right, let's do B. Let's calculate the kinetic energy of this. Now I'm going to do this the long way the first time through. And then hopefully a concept will pop out at you. So we're just going to use KE equals 1/2 mv squared. 1/2 911 10 to the negative 31st times V squared, which we just found, right? What was our V? 6.5 times 10 to the 6. Squared. Let's go, quick.
1.92.
Okay, joules. But I asked it for you in EV, so let's divide by 1.6 times 10 to the negative 19. Gives us 120. That looks interesting. Where did that answer come from? Why is it 120? So notice, remember the definition of an electron volt is 1 volt given to 1 electron. Well, if you give 120 volts to an electron, it should have an energy of 120 electron volts. Okay? Use that concept for future problems. All right, letter C, we're now going to find the de Broglie wavelength. Okay, so we're just going to use lambda equals h over p. 6.63 times 10 to the negative 34th divided by the mass of an electron times that velocity that we just found. 6.5 times 10 to the 6. Okay, help me out, guys. What's wavelength?
1.12 times 10 to the negative 10.
All right, so notice that our wavelength, it's still small, but this is at least reasonable. This is something that's decent that we can actually use the double slit with. So for part D of the problem, we're just going to use our double slit concept. Okay? And I'm just going to skip a step here and just tell you that this is going to be a small angle. So x over L equals m lambda over d. To truly do this, you should prove small angles, but I'll just tell you in advance that it is small. And let's go ahead and solve for d. So x was 0.1, L was 2, m is the first order, wavelength is 1.12 times 10 to the negative 10, and d is what we're looking for. What are you guys getting for d? Did you say 9? Okay, look at that, perfect. So that would be the slit spacing here, the distance between them.